Hi, welcome to the analysis, design, and simulation of a Flyback Part 6. In the last video, I derived or actually included the efficiency, and also picked a more realistic duty cycle, and just I guess a recap of the specification. The power output is supposed to be 6 watts, and accounting for the efficiency and assuming an efficiency of 80%, then we can calculate that the input power is going to be 7.5 watts. From that, you can calculate the average input current, divide the 7.5 watts by the minimum input voltage, which is 24. We get 312 milliamps. From that, we calculate the input peak current, and this is where we assume a duty cycle. Actually, it's not an assumption. We picked this from a data sheet. Okay. So from there, we calculated that we should have 1.35 amps. And then we calculated the time on. Okay, since we have a duty cycle of 0.46, we can divide the frequency, and we should get the time on. So in that case, it's 4.6. And once we have that, we can calculate the primary inductance. So in this case, to achieve working Flyback, we should design the primary for 81.7 microhenry. Here we have the kit from Worst Electronics. It's a speedy design kit for power transformers, medium powers, 15 to 30 watts. What's neat about it is that it comes with the cores. It's got the EFD20 cores, EE20s, 25. Also has the bobbins. Sure. So these are feed through. They also have, I believe, some that are surface mount. Also comes with wire. Here's a gauge. Let's see, 0.1. And see, the gauge is 38. And let me see. And once you have that, it also comes with wrapping tape that you can use as an insulator. So it's a pretty good kit. Now, in looking at the book, let's see if you can zoom in there. Okay, these kits, if you use a ER11 and you use a Flyback topology, it's capable up to 8.5 watts. I'll be using the EE20. With the EE20, it's good up to 70. Let's see. Can zoom in or not? Okay, it's up to 73 watts. And that's the one that I'm going to use because it's large enough where I can wind it by hand. Okay, so one of the things that you have to, before you wind it, you have to calculate how many windings on the primary. So there's this equation, which is the turns ratio has to be greater or equal to the primary inductance times the I, the current, or the peak current, times divided by the BSAT times the effective area of the core. So in this case, in this particular material, the BSAT is 360 Telsa, or 3600 Gauss. And for the EE20, the area is 32 millimeters squared. So when you plug in the number, here I have 81 microhenry, and here's my peak current. And what I did is, instead of using the peak current or the BSAT of 0.36, Basically, I went ahead and used a slightly lower. Basically, you're gonna have a hysteresis that looks like this. This part is the BSAT. Okay, so you don't want to be operating in this region. So you want to operate in this little area that's kind of linear. So I'm picking this to about to be 300 instead of the 360. That way I have a little bit of margin. So with that, I end up with a turns ratio, or a turn in the primary, of 11.39. So what I did is I rounded off to 12 turns. And since I have a turns ratio of 0.5, all I have to do is divide 12 by 2, and that will be the turns ratio of my secondary, which is 6 turns. Okay, here I have a core, well, not the core, but I have the two EE20 cores, and this is how they sit, or the shape of them, and they go in the bobbin like so. So it kind of looks like that. Okay, so that's the area, and if you notice, that's the area. So what I did is I went and got a dowel, regular dowel that you can get in any hardware. It's a round one, and what I use is I used a little sander, or you can use a knife to whittle it. Basically, you make a little square shape where it fits. Okay, it's nice and snug. Now, luckily for me, that the turns is only 12, which is something that you can do by hand. You don't have to use a winding machine, although you do have to keep track. So in this case, I'm using this wire, and I believe it's a gauge 26. It's an enamel wire, and what I'll do is I'll go ahead and make a couple of turns, and probably even put a little piece of tape, and once you start turning, start winding, and in this case have it like that. So that's the start. So I have 1 and 2 and so forth. Excuse me. And you wind it until you have your turn, your 12 turns. Okay, here's the bobbin. I went ahead and wrapped 12 turns of the wire. If you notice, there's some spacing in between. Actually, there's enough space that I could have used 2 wires. When you use 2 wires, it's called bifilar. I would have completely filled the bobbin, and probably give you better coupling coefficient. But since I just want to do something as simple as possible, this is good enough. The next step would be putting the wrapper, so that would be the next step. Here's the wrapper. It's for the EE20. Let me take it out. And it should be approximately the same width. So we'll go ahead and wind it. That way it offers isolation between the primary and the secondary. Okay, here it goes. Not too bad. So that's 1 winding, and then just give it a little bit, an extra half turn. Cut the material. Okay. And sure, so that's the isolation. Okay, so we're done with that. So then we're ready for the next, for the primary. And in this case, since it's a real simple design, I'm just going to do 1 secondary. Again, go ahead and wind it. and I'll put it in this section and go through there. Okay, and then wind it. Okay, here I have the 1, 2, 3, 4, 5. We do 6. 1, 2, 3, 4, 5, 6. Yes. So that's the secondary. So I'm going to wind the primary or solder them here, primary, and the secondary will be here. Okay. So now all I have to do is put another piece of tape on the outside and then solder the wires. Okay, I went ahead and put the wrapper. Okay, so I can go ahead and put this. I'll have to use a little scraper and then solder these in, and that'll be the next step. Okay, now I went ahead and put the two cores, and since they're not capped, you're gonna have a higher inductance. I'm shooting close to 80, and right there, that's the primary. So as I hold it together, reach about 172, 76 microhenry. So that means that I have to grind the core. So I'll do that, and it's kind of iterative. I have to go back and forth and measure. Okay, here's the grinding machine. It's actually a drill press, and it's got a little diamond tip, and we usually fill this with water to keep the dust, and then put it there, and we turn the grinder or the drill press and then press it, and then put it back, clean it, put it back in the core, measure the inductance, and if it's still too high, we do the same step back and forth until we hit our target area. So as you can tell, I may or may not be able to tell. Let's see if I can do the macro. Well, you can tell that right there, it's a little bit shorter, or at least the center has already been grounded to the gap that we need, that will give us the 80 or close to 80 microhenry. Okay, here's the finished product. I have the transformer, and then measuring the inductance. The inductance target was about 80 microhenries, and as you can tell, it reads 77, which is kind of close. So I'm not going to worry too much about it. It'll give me a little bit more power since it's a little bit lower. So, and what I did is right here I added some pins because I have some sockets on the printed circuit board, so this makes the insertion or the extraction of the flyback much easier. Okay, I went ahead and put the wrapper around the core, so now it's being held together. Now I'm switching over to this LCR meter, which has a little bit more resolution. What I want to do is I want to measure the coupling coefficient. So in this case, it measures very close to what I was getting with the B&K, but because it has more resolution, I'm using this one. This one, by the way, is LCR by Almost All Digital Electronics. I think it's a fairly good LCR meter, or actually it's a LC meter, so I highly recommend it. So right here, the measurement is 77.92 microhenry. So to figure out the leakage inductance, you short the secondary. So here's my low impedance. Hopefully it's enough of a low impedance. Short out the secondary. Okay, so now the secondary is measuring 1.57 microhenry. Okay, so that's actually the leakage inductance. So if you look in here, LP is 77, and LK is going to be 1.57 microhenry. So this is the actual series inductance that would be uncoupled. Okay, when you plug in the leakage inductance and the primary inductance into this formula, you get the coupling coefficient. So this is a coupling coefficient that you would use in your SPICE model if you're using the coupled inductor. So it would be 0.98987. Typically, if you can go to the 4th or 5th digit, you'll get very good results in your SPICE simulation. Okay, the next parameter that I want to extract is the parasitic capacitance, or the self capacitance that is in the winding. I'm not talking about from secondary to primary, but within the primary. One way of doing it is by hooking up your power supply. In this case, I have a capacitor here, and the reason I have a capacitor here is that I want to have enough charge here, and when I actually put 1 volt across the primary, I don't want the current limit to turn on, or at least current limit to be enabled. So I put the cap to have enough stored energy to allow me to do the ringing. Basically what I want to do is I want to do a little step response, and what I have here is I have the primary, I have the scope connected here between the primary, and then I have the ground of the power supply here, and I went ahead and I'll redo this. I went and set the, let's see if I can, I put the coupling, or actually the trigger mode to normal, okay, DC, and should be ready. And anytime I click it or touch this, and as I hit it with a voltage, it should ring at its natural frequency. So if you notice, it's a little ringing. So you can get a big one. Okay, if not, that's good enough. Get another one. Okay, that's a good one. So now I can use the cursor to measure the frequency. Let's see, how is this done? Cursor, and let's see, X, okay, put that peak there, and then I have that. Go ahead and expand it right there. So I have a frequency of, let me see, what's the frequency? I believe it's 20. Let's see. I gotta figure out what the frequency is. Okay, had a little senior moment. It looks like the delta X is 4.5 megahertz. So that's the ringing. So once we know what the frequency is, we know the inductor, we should be able to calculate what the capacitance is. Okay, so knowing the inductance, which is 77 microhenry, and the primary, and the frequency is 4.5 megahertz, we can plug it into this equation. So I come out with 16.26 picofarads. So basically we have the inductor, or the transformer, that looks like this. and we have a leakage inductance, and I believe it was 1.57 microhenry. This primary is about 77 microhenry, and in parallel with all of that, you have a capacitance of 16.26 picofarads. So you can include this in your splice model, or you can use the K factor. That will introduce the leakage inductance, but you also do have to add a 16.26 picofarad across the entire winding. Okay, now that I extracted the parameters of the transformer, I define the leakage inductance by using the K factor. In this case, I go to the K model and I put the 98.98.7, and you can see that right there, and that automatically will add a series inductor in series with the primary inductor. And since it's in series, the self-resonant capacitance, or the parasitic capacitance that we calculated, should be about 16 picofarad. That is added there. Okay. And then the MOSFET that I'm using is a IRFF220, so that is added there as well. Now, as soon as I'm done with the simulation, I will be putting I'll be connecting a function generator, and since the output of the function generator is 50 ohms, I put 50 ohms in here to simulate the impedance of the generator. And again, I define the turn on by the duty cycle divided by the frequency, and the period as 1 divided by the frequency. And I believe I have everything. I have that, and once I simulate it, okay, I look at the drain, and as mentioned in a previous video, should get a little ringing, and as you can tell, that's quite a bit of ringing. That's the drain. Okay, so during this time the MOSFET is on, and then as soon as the MOSFET is off, the MOSFET releases it, and you got this ringing effect. Now remember, this ringing is because of the leakage inductance and the capacitance from the drain to the source. So that accounts for this ringing. Okay, so now that we have that, we can go ahead and expand it. Oh, one other point, as this is the time on, and then from here to here is the time off, and if you notice here, it stops ringing and then the voltage drops. That means that the transformer has reset. Okay, in the next video I'll discuss it a little bit some more, and we'll actually see it on the bench. So let me go ahead and zoom in. Okay, there's the ringing, and if I go to the cursors, cursor there, put a cursor here, and according to this, it's ringing at 17.2 megahertz. So now we know the frequency. So now that we know the frequency and we know the inductance, we should be able to put a number across. Okay, we'll do it in the simulation, and we'll also do it in the breadboard, see how well they match. So in the next video, I'll test the transformer, and I'll compare this waveform the waveform of the drain with scope shot and see how close we modeled the transformer. Again, thank you for watching, and stay tuned for the next video.